Oh, it's on. And now we'll stick to English. So yes, I'm George Neville Neal. I'm the person in blue. This is very loud. I'm going to hold this here. This is research work we've been doing at Yale University with my advisors, Robert Soleil and Alvi Silverschatz, Peter Alvaro at UC Santa Cruz, Alex and Stelios are other students with me on this work. So let's start with the question. So I have spent most of my career being an engineer and not a scientist, and there's only one difference between scientists and engineers. Engineers actually build stuff, and scientists go, huh. So now I have to go, huh, a lot. And so the question we're trying to answer in this research is, well, not why would anyone do this, although it's the question I asked when my advisor suggested it, but what are the things that we can see if we apply these two technologies to each other? So why would anyone? So I don't know if this is true, but there are a lot of people talking about the relational model. There's quite a number of papers on this. In particular, back in the 80s, one of my advisors, Avi, proposed using a query processor, like SQL, to replace the shell. So instead of having the Bourne shell or some other shell, you would simply talk to the system as if it was a database. And there's now a tech report on that. But lots of other people have thought about, well, we have this model, the relational model. It has some very nice mathematical properties. Why don't we apply it to various pieces of software besides just databases, including operating systems, and including us. So this is a paper we had at CIDR this year, and this is the basis for some of the talk. So if the relational model is so awesome and great for operating systems, where is it? So there's a lot of problems. First of all, operating systems are huge, 20 million lines of code, 90% of which is device drivers, depressingly. FreeBSD is a little smaller, 10 million lines of code. And other people have taken other approaches to this. In fact, the database people think that they don't need operating systems and that they can just throw the operating system out and manage the hardware themselves, and they'll do a much better job of it. And as you can see over the last 50 years, they've done an excellent job. No. So why has no one done this? Well, for a bunch of the reasons listed here. These systems are large, they're complicated, and they're fragile. So one of the things I'll be talking about a little bit in this talk is less about the science of what we did, although I'll talk about that, but also what it's like to do research on open source software, using open source as the basis for scientific research, not just engineering artifacts. So it turns out that that operating systems, and actually any large program, we've applied this technique to a bunch of other programs now, but the operating system actually has a database, right? So an operating system very, very generally has all these crazy device drivers that make all your network stuff work, usually badly. And then this generic kernel state, right? So is that me? Okay. Okay. I am really enjoying the construction outside too, by the way. That'll show up on the recording. Anyway, so operating systems, large programs, they already have state. They have a ton of state, right? You have the scheduling, you have the memory management, you have files, you have all of the things that the kernel is maintaining so that so that an application programmer can write applications and pretend that the computer is their own. And we spent the last 50 years doing this. So the OS already has to manage its internal state. And if you view that state in this way, the OS really is a database, but its query methods are, this is the polite term, ad hoc and idiosyncratic. They're not very good. So how do we query the operating system now? Well, we have a bunch of system calls, 500 of them. We use config files, and then we receive unstructured text. And this is one of the things that's interesting to us for our research. A lot of what people do when they're trying to understand system performance and system deployments and systems generally is take a massive amount of text and then they put it into Splunk or some other thing that crunches that text to tell them things about the text, which is kind of a strange way to deal with a computer, which is very accurate about what it does. Right? The computer actually knows. The operating system knows what the state of the system is. And then it turns that into a stream of bytes. It's like, here you go, good luck. Okay, every time I move, I'm like, thinking someone's out to get me. So let's think about something really simple. Now, this is a systems track, so I suspect everyone knows the answer to how you would actually do this. Please don't call it out. But the classic thing that a student will do when they write their first networking program is they run it twice. The second time they run it, they're like, oh, why won't it run? I get this thing called EADR in use. And then they run around going, well, where's the other program? They want to find the program that's bound to the port and they want to kill it. So that sounds easy enough. But if you're naive, if you've just started using the system, if you're not a systems programmer or a Unix person or whatever, then you've got a bunch of choices and not a lot of good ways to find out, because the way that the operating system represents things to you is ad hoc. I guess I'll keep talking. So, if you're on one type of system, you would call task list, but let's not talk about Windows. Even if you know that it's PS, right? Even if you know that PS means process status, which most people don't. They're just like, oh, I always call PS. What are the arguments, right? So there's no regular way to access the data in this kernel, right? You have to know a whole bunch of what we call arcana, a bunch of random stuff, in order to effectively use the system, which is not the way databases work. And then when you get things back, you get this unstructured stream of bytes. So on the upper side here, we've got netstat. On the lower side, we've got PS. And if you notice that there's no correlation, there's no process ID in the network listing, and there's no network listing in the process ID. So you have to figure out some way to do what database people call a join, right? And the way we do join is with grep. Right? We pipe all this stuff to it, and then we're like, grep. Very inefficient. So what do we want? Well, we thought, okay, well, if we put a relational interface into the kernel, then we can actually query it with SQL. And SQL is a really ugly language. It is the COBOL of data analysis. For those of you who are old enough to remember COBOL or who've been forced by old people like me to look at COBOL, it's not a pretty, it's not like I'm saying, oh, this is beautiful. But it is regular and it is used everywhere. So the nice thing is that it allows for this incremental exploration. You can actually say to the kernel now, tell me what tables you support. Tell me what columns are in the tables. Tell me what are the data types of those columns. And you can do what we call the programmer as navigator, which is a classic old paper from the 70s, where you can incrementally learn about the system. It has some other nice side effects of doing this. One is we can preserve the native structure of the data. So instead of taking a bunch of integers and reals and other things from the kernel and then splatting them out at you in text and then going, oh, well, I'm going to grep through that. We actually preserve the native structure of the data. And again, the most powerful bit is this thing where we can join. So how did we do this? Let's mix two code bases. Let's take 10 million lines of code and 50 or some thousands of lines of code and smash them together at high speed. I mean, it's always nice when your advisor says things like, oh, it's just C. I'm like, yes, it's just C. Luckily for us, well, I've worked on FreeBSD, so I have a bias. This is a really well-written operating system. And actually, SQLite was written to be portable. So SQLite is in almost everything. Like once we did this, I discovered it was like cockroaches. Like you just like lift things up and there's an SQLite in it. Python has SQLite built in. Both debuggers, LLDB and GDB, already have SQLite in it. It's just everywhere because it's small and it's portable, which is great because it made it, I would never say easy. It made it less horrible to port it into the FreeBSD kernel. So what we wanted to know from an engineering standpoint, not from a science standpoint, was how can we expose our kernel data without rewriting the OS, right? There are these proposals out there. There's a system called DBOS, which is proposed by Stonebreaker, who's a very famous database guy. We're like, we're going to rewrite everything from scratch. And I'm like, Mike's older than me. Like Stonebreaker's in his 80s. I am not going to live long enough to rewrite all of FreeBSD in something else. In fact, I don't want to live that long. That seems like a long time. So we wanted to be able to do this incrementally. We wanted to be able to go table by table, data structure by data structure. How do we model the kernel state? So you look at the state of an operating system kernel, and the only way to model it is to ask a person, which turns out was me. Hey, GNN, how does that work? And then do it incrementally. And then here's the hard part. So here's the fun bit, one of the fun bits about research. So in research, the idea is the important thing. You can have a terrible implementation, but as long as the paper is good and the graphs look fine, nobody cares, which is really, as an engineer, very frustrating. Because for me, I've spent 30 years working on operating systems, and correctness, super important, because as McCusick says about the file system, if you lose someone's data once, they never trust you again. But in research, whatever, just reboot. And so it was a very interesting set of discussions. I do not argue with my advisor, but we do discuss. Because we wanted to be able to do this. How do we make sure that the kernel's not going to crash or trash data or give it an incorrect result while doing all these crazy things, basically while changing bits of the airplane while it's in flight. And so one of the beauties of open source, of course, is we've got the entire source code, right? I can now look at all of the source code. But it's 20 million lines of code. Like, who wants to do that? Without open source, we would not have been able to do this as easily. We would have had to pay Oracle to let us mess with their database, and I'm sure they would have been thrilled. So from an implementation standpoint, SQLite, FreeBSD, for those of you who don't know, it's embeddable, so it's everywhere. So one of the nice things about SQLite from an open source project standpoint, first of all, it's a very small group. I think there's like 3 people, and there's one person, Dr. Hip, who answers all the email. Oh, and if you want a really amusing slight side thing into licenses, go read the license. SQLite's license is not a license. It is a blessing. It's like, I don't give you a license, I give you a blessing. I'm like, whatever. But SQLite also has some features we really wanted, and in particular, this virtual table mechanism. So in SQLite, you can map any data structure that you can access and see into something that looks like a table by implementing a bunch of methods. That's called a virtual table. And we use this all throughout our work. And then we ported it to run in the FreeBSD kernel. And the reason that that was possible is SQLite not only has been ported into a whole bunch of user space code, which is a lot easier for those of you who've done both user space and kernel. In user space, you're like, oh, the program crashed. I've got a debugger. On operating systems, the program crashed, and now I have a red light. But they had ported it to VxWorks, which is a long-standing embedded RTOS, one that I worked on actually back in the late 90s. And so I knew they actually had the right hooks for things like memory management. Like, how do they get a block of memory, and how do they deal with timers, and how do they deal with a whole bunch of things that the operating system provides. So we were able to port that into FreeBSD. We use FreeBSD because it's a well-known Unix clone, developed over way too many years. I actually didn't have gray in my beard when I started. I didn't have hair, but I didn't also have gray hair. And it's well documented. So one of the things that's really nice if you're doing research, and one of the papers that I'm supposed to finish, which I haven't finished yet, discusses how you use something as big as FreeBSD in your research. Because most people will take a Linux or a FreeBSD or whatever, and they'll do some changes to it. They'll generate a graph, because that's what scientists do, and then there'll be no more work on it. And so having documentation that talks about this is sort of one of our next steps. And there are people who've done this well, right? I mean, BSD, the original BSD, not FreeBSD, like BSD when I actually did have hair, like that long ago, was developed as a research project for DARPA, right? Those people wrote papers, they were doing science, or science plus engineering. They're not physicists. If I had been smarter, I'd have been a physicist. I'm not that smart. So it has this history of being used in this way, and that really helps. So what do? We took this incremental approach. Well, we don't want to rewrite 20 million lines of code. We took SQLite, and you saw what we did with the Meteor. We smacked it into FreeBSD. We killed the dinosaurs, I guess. Sorry. But the trick, and I'm going to walk in front of the camera because I can't stand still. The trick was to use the existing structures as tables. So here's one of the nice things that I'll talk about C. So C is basically memory access, assembly language, and for loops, right? It is not a high-level language. Don't believe what people tell you. And so we used the existing structures and we didn't change them, right? So not only did we not write a new operating system, I'm gonna throw this across the room. Not only did we not write a new operating system, but we did not change the underlying tables. The process list is still the same data structure you would see in the FreeBSD book, which I co-authored, or in the source code today. We did not modify that, which is good because I don't want to live that long. I mentioned this approach last year in a keynote, Ship of Theseus, which is the ship brought home from Troy, I guess. I don't remember anymore. Anyway, Ship of Theseus is we keep changing bits of the wood because it rots. If we change all the wood, is it still the same ship? If we change all the wood in the kernel, is it still the same ship? So why could we do this? I talked about, there's many people running around now. I talked about the fact that this is all in C, right? So SQLite's in C, FreeBSD is in C. And I'm still speaking. Okay. And so when you think about what you have in the relational model, like a table, or a row, or a column, foreign keys are a little more complicated. I'm not going to go into that. They're basically the ability to point to something else in another table. But a table is just a list. In the kernel, it's a list of C structs, right? Struct proc, blah. In fact, struct proc is over 100 lines long, which really depresses me. So you have this list of structures. In each C structure, that's one row. Each field is a column. This maps exactly to the relational model. Like this produces a table every single time. And operating systems, I don't remember if I put this on the next slide, are not only large, nope, we'll go back to this one. Operating systems aren't just large corpuses of code, but in order to be efficient, they're simple. Like we do not have, so all of the complex data structures, I keep putting big scare quotes, in FreeBSD are in one file, q.h. In q.h, there are lists, doubly linked lists, tail queues, and that's it. So for those of you who took computer science undergraduate and people told you about these beautiful data structures and trees and red-black, and there's none of that in the kernel, like nothing complicated. So that makes life for this particular project a lot easier because everything in the kernel is a flat table. The only tree we've ever really had is the routing table, which is a trie, and that's it, at least in FreeBSD. So now we have to talk about semantics. Good, I've still got time. So I talked about the correctness part. Well, read-only is simple. Like for those of you who took computer science undergraduate, you remember when you did your first thing and you were like, oh, read-only access is something. Oh, the locks are really easy. It's all really fast. Great. So one of the things we don't want to do is hold a lock during the query. Like if I'm going to say list all of the processes, I don't want to grab the process lock from user space and just sort of like hold it while I read data out of the kernel. That seems really bad. So instead we use the snapshot approach. Right, we take the data structure, we take all the memory, we just do a memory-to-memory copy, we move it over here, and then we operate only on the copy. And that means we hold the lock for the shortest period of time. And we use the kernel's locking mechanisms. Like, of the things I do not want to do with the rest of the time I have left on this planet is to write another set of mutexes. Once is enough. Don't want to do that again. So we use the kernel's in-kernel locking mechanisms. We actually say, go lock the table, give us a copy, unlock. So snapshots are transactionally consistent time series, right? This gives us a really nice way of looking at data. So I can actually sample the data in the kernel for like 30 seconds or 5 minutes or however much memory I've got to do that. And then, for instance, if we crash, let's say we're trying to debug a kernel crash, I can actually capture the last number of snapshots before the crash. And when we do, when we panic and we do what's called a dump, we dump everything to the disk before we reboot, I now have that in memory. Now this is all feasible because kernel state is small in database terms, right? So people who build big, I don't know, AI models, whatever those people do in user space, that's a lot of data. But Kernel data is small, right? So all of the processes, all of the pointers in the virtual memory system, all of the sockets, the only thing that's even been challenging to store in memory is all of the V nodes in a big file system, right? So in a file system, every block is identified by a node. So if you have terabytes of data, you have a lot of nodes. That's challenging. But everything else, peanuts, because computers are big. Memory is big, and memory is cheap, or at least cheap, versus when I had darker hair in my beard. So read-only, pretty simple. Lock the table, make a copy, operate on the copy. But we also wanted to do update. And someone before the talk was chatting with me and asked about this other technology that exists called OS Query. So OS Query is a user-space program that represents data from the kernel, data from system calls, using SQL semantics. And OS Query is quite cool in that way. It has a lot of challenges that we've surpassed because it's not in the kernel, it's not as fast, lower fidelity, a bunch of other issues. But also it can't do an update, right? So one of the things you want to do when you've got this transactionally consistent way of handling the data is now I want to be able to make changes. fight over the cache, and they fight over memory. And so you get really poor performance, you get really bad jitter between if you're doing high performance computing, which is what I was doing when I did this for one research. I'm going to try this now in my last 5 minutes.
It's okay, just keep going.
I'll keep going.
The break time is for you.
That's fine.
Yeah, it's break time.
Anyway, so being able to do that, we could also do what's called an out-of-network checker. So if you've ever accidentally run a runaway process on a Unix and memory grows huge, and then the kernel's eventually like, and shoots your, I didn't mean to shoot you, eventually kills your process because you've used up all the memory. So we wrote, without changing the kernel, an out-of-network checker. So imagine someone wrote a program and it's being flooded by a DDoS, right? But how do I get to the thing and make it quit? How do I get it to stop so I can actually log in with SSH? Well, if you have this thing running on your server, then it will do that for you. It will kill a process that has used up too much network bandwidth. And that's why we see message send here. And 10,000 messages is not a lot, but again, in research, I don't have to actually have a production system. So we did some overhead calculations. We were very surprised that adding all of this weirdness to the kernel didn't break it. Where these lines are is not important. That these dots don't move is. As we increase the sampling frequency, asking for more and more and more and more snapshots, the performance of the system overall didn't change. Which, as a systems person, I'm like, oh, right, memory copies are cheap. I'd written them to disks, they would have been different. We found this weird thing, which is OSDB is faster than PS. So we cranked up, we basically suspended 6,000 processes and read the process table with PS. And I saw this graph, and so there's another one in science, right? In engineering, you're like, well, I guess we should both be skeptical. But you're like, oh, this graph is great, let's publish. And the engineer in me is like, that graph is wrong. And it wasn't wrong. It's because of a couple of reasons. One is PS uses a lot of time in QSort. Remember early on, I mentioned that one of the challenges, one of the problems in current sort of OS telemetry or systems telemetry is we suck all this text out. Well, that's what PS does. PS pulls all this text out of the kernel and then runs QSort on the text. And the larger it is, well, QSort is worst case O of n squared. That's the red line. And we use SQLite, which uses merge sort, and it's sorting not on text. It's sorting on integers. Cheap. Integers are cheap to sort because computers love integers. They don't love text. And its worst case is O n log n. Ta-da. Was amusing. So for our work, did we answer the question? Yes, we find that a relational interface benefits the OS. It's standardized. We can add new functionality via SQL joins without having to rewrite the operating system. Open source totally supports this approach. We were able to embed this query processor that's been, SQLite's been around almost as long as FreeBSD. It's a very well-used piece of software. It gave us this incremental solution, and we could reuse existing kernel mechanisms. Now, extra punchline. So let's talk about the joys and sorrows, color-coded for Christmas, because red and green, of working with open source in research. So there are some great things, right? I have complete control over the source code. Of course, there's a downside to that, because then your advisor says, you have complete control over the source code, why don't you change it? I'm like, dude. Anyway, and now fast computers make development easier. So I was really psyched to see that Framework is one of the sponsors of the conference, because they donated a bunch of laptops to the FreeBSD project, and they're really nice. And my other laptop is a Framework laptop. It's really cool. And they're fast, right? Computers are fast now, right? I am an old person. I remember when computers were slow, and I do not miss the old days. I can build all of FreeBSD in an hour, and if I didn't have to rebuild the compiler every time, I could do it in 10 minutes. I can build the kernel in 160 seconds. And the SQLite stuff doesn't take very long. All this open source stuff works really well. But there are some really problematic downsides. So when you're working with open source software and you're doing research, research takes months. It took us 6 months to get the paper out on this. In 6 months, FreeBSD had a stable release. The head of the tree moved every single day. People were making commits. We were trying to track the head of the tree, which, you know, there are companies that track the head of the tree, like Netflix, which uses FreeBSD. But they have a lot of people paid a lot of money. And I'm a graduate student. So that's the opposite of a lot of people paid a lot of money. So keeping up to date with head is hard. I think the advice is to stick to a stable branch of whatever OS or code base you're using, because most open source projects, no, that's unfair. A small number of very mature open source projects are committed to stable branches, FreeBSD in particular. There's this challenge of research prototypes versus shippable code. One of the things that academia, or actually that ACM and other publishers have been pushing on academia, which makes me super excited, is to force people to share their artifacts, right? So in science, you can't just say, I made a thing. Like Lawrence, who made the cyclotron, didn't just say, I made a cyclotron. He made one, and then he extracted uranium. So traditionally, researchers have been able to get away with like, oh, here's the graph. And then you go look at their GitHub, and you're like, that code doesn't work. So there's this tension between research prototypes and shippable code that continues to be challenging when working in research. Because as someone who's spent their life making shippable code, I'm like, yeah, we made the graph work, but I wouldn't give that to a person. Certainly not someone I like. And then we have this challenge of measurement and reproducibility. So open source is great because you have all this access, but also it's huge. Like measuring an operating system is hard, right? And measuring it in a way that is scientifically valid is really hard. And in fact, I would argue, I probably shouldn't say this considering I got away with writing a paper about it, that it's something that we don't do very well. Scientists don't do very well. Like a physicist who said that the Higgs boson was X and got it wrong, you know, 1,000 other physicists would be like, dude, or dudette, you know, whoever you are, you're wrong. But in systems work, we kind of like throw out these graphs and people are like, oh yeah, that looks right. You're like, really? Why don't you rerun the experiment? So this is a challenge for us with open source because the artifacts are so large. And it's actually why, if you look at a lot of traditional OS research, people always make their little OS. They're like, oh, I built a little OS. And you're like, right, because it's small enough to be tractable. But if you want to do research on something like a Linux or a FreeBSD or a big system, and you want to do that because you have impact, right? Like if I do something good on a BSD, I'll always be in FreeBSD because I'm not going to live that long. Then someone else can pick it up, and then your research has impact, and that's great. So some of the issues there. We're actually going to put it on GitHub. Actually, it's currently in a private repo on GitHub. There's a Linux port. We've been looking at doing some eBPF stuff. If you really want to hear 8 more minutes of my voice, which I don't know that you do, scan that. There's a demo of all of this stuff working. And that's it. And I'm way past time. And I think this is now dead, by the way.
No, it's
This is
actually
really
working.
quiet.
Yeah, it's working. Just for reason.
Okay.
Do we have any questions?
So, interesting question. We are modeling only the OS state. Our current next set of research is actually looking at applications and the OS at the same time. So distributed queries between something in user space and the kernel to try and correlate what's going on across the user kernel boundary. That's actually our next set of research, which I was working on 2 days ago. So the difficult part isn't getting the transactions right because of the snapshots. Once we decided to do snapshots, we're transactionally consistent. What is difficult And one of the other things that we actually just had a paper on, wouldn't say difficult. The thing that I really want us to do more of, and I hacked something together to do this, is automatic extraction. So right now, I don't know if everybody knows the word bespoke. Like a bespoke system is like completely hand built. So all of the tables that you saw, some idiot, me, had to go, oh, poke, pull them out, and I did it by hand, right? I wrote these things by hand. What you want is kind of like what dtrace does, and eBPF a little bit, but the dtrace system is really good at this. It leverages the compiler to look at the source code and pull data out. And we've got a Clang plugin that someone built so that it can look at the kernel and be like, oh, you have a list here. I'm going to pull that out, that whole thing out, instead of just having a programmer do it one by one. So the big thing for us actually is to get more data, more columns automatically. And what you really want, the thing that I love that dtrace always did, was if you use a compiler to do this, every time you build the kernel, you get the correct data. Because every time you build the kernel, the compiler goes through and is like, oh, you changed this structure. Now I have to expose this structure again. So that's the big one for us. But transactions, so long as we use snapshots, aren't, I wouldn't say they're easy, but the query processor handles that for us. I think I should probably give it over to the next person. Thank you.